Hello, guys. Right now, I'm chilling on my couch. I'm a little bit tired. And I'm gonna try a new kind of style of 7 minute summary. I'm doing this on my phone. Here's the PDF of the Survey and Jowett book. And I hope this looks good on YouTube. I'm just doing it to show y'all that you could do this anywhere. If you have a laptop, if you have a phone, even if you don't have this PDF, just go online, search up physics PDF free, put in like the chapter that you're looking for. Or if you want this book specifically, you could search up Physics for Scientists and Engineers, Survey and Jowett, free PDF. Or you can type file type colon PDF, and you will find a bunch of free PDFs, and you can save them to your phone, and you can read them anywhere you want. So let's take a look at this. It's going to be a 7 minute summary. I'm going to just quickly look at the sections over here. Let's zoom in. Chapter 43. It is molecules and solids. Molecular bonds, energy states and spectra of molecules, bonding in solids, free electron theory of metals, band theory of solids, electrical conduction in metals, insulators, and semiconductors. Very cool. Semiconductor devices gets its own section, and it ends off with superconductivity. Very cool word, very cool phenomenon. Superconductivity straight out of a sci-fi movie. Anywho, that is the stuff here. This is normally how I do my 7 minute summary. I'm gonna pull up my little Google Assistant.
All right.
Whoops. Okay, let's get to work here. So, the most random atomic arrangement, that of a gas, was well understood in the 1800s. As discussed in our study of kinetic theory in chapter 21, I have not done that on this channel. It's kind of thermodynamics, I would assume. In a crystalline solid, the atoms are not randomly arranged. Rather, they form a regular array. The symmetry of the arrangement of the atoms both stimulate and allow rapid progress in the field of solid-state physics. Okay, let's move on here. Molecular bonds. Okay. Man, I don't want to read too much. Let's just take a look at this function here and take a look at the accompanying graph and read this graph over here. So we got total potential energy as a function of internuclear separation distance for a system of two atoms. And we see a lot of stuff here. So binding energy, I see kind of in the middle right over here. I see total potential, attractive potential, a bunch of stuff, but this looks like we're talking about energy, right? Because they're talking about total potential energy as a function of internuclear separation distance. So keep in mind, we're talking about energy here. Ionic bonding, when two atoms combine in such a way that one or more outer electrons transferred from one atom to the other, the bond formed is called an ionic bond. You may have learned this in a chemistry class. Ionic bonds are fundamentally caused by Coulomb attraction between oppositely charged ions. Interesting. And we got a similar looking graph over here. You see why it's important to look at the graphs? You're going to see a lot of these come up. It looks like we got some sodium and some sodium chloride stuff going on here. I'm not too sure. Let's read over here, pitfall prevention. Those are always interesting. Ionic and covalent bonds. In practice, these descriptions of ionic and covalent bonds represent extreme ends of the spectrum of bonds involving electron transfer. In a real bond, the electron may not be completely transferred, as in an ionic bond, or equally shared, as in a covalent bond. Therefore, real bonds lie somewhere between these extremes. So there's ionic bonds and covalent bonds. I don't think I saw covalent bond mentioned anywhere here. Is it here? Oh, here it is. Covalent bonding. This is the next one. And it looks like this equation is a quantum mechanical equation with the little psi over here. You remember the psi from the previous chapters? Anyway, that might be important. We got some other graphs here, but we're not going to look at them too much. Van der Waals bonding, so I guess another type of bonding. So in total, we have ionic bonding, covalent bonding, van der Waals bonding, hydrogen bonding, and it looks like that's it for the first section. So we're just going to keep those big sections in mind and move on to energy states and spectra of molecules. So we got some energy addition here. I'm not going to read that. There's a little picture of a DNA strand there. Cool. Rotational motion of molecules. Let's consider the rotation of a molecule around its center of mass. Whoa, that is a crazy thing to look at. This kind of, I remember this from kind of a classical mechanics course. When things are rotating, you got moment of inertia and stuff like that. Here it is. I is the moment of inertia. So if you don't remember that, no stress. We're going to take a look at it in this chapter. But let's zoom through. We got some similar looking graphs here, the energy of allowed states, which we saw in the previous kind of atomic physics chapter. But we only did a 7-minute summary, so we're not really too comfortable with all of that yet. Let's take a look at these important equations here. We got reduced mass of a diatomic molecule, okay? Allowed values of rotational angular momentum, allowed values of rotational energy. Okay, so it looks like the only one that's yellowed out is this allowed values of rotational energy. We got some J's. We got an H bar over there. H bar is normally associated with quantum mechanics. I don't know what the J's are, but anyway, a buildup of quantum mechanics. Let's read this as well here. Energy of a photon absorbed in a transition between adjacent rotational levels. What does that mean? I'm not sure. Let's take a look at the first example, rotation of Cl molecule. Cool. Vibration, motion of molecules. Another kind of interesting equation. We got EVIB, vibrational quantum number, energy of vibration or something like that. Who knows? Here's another graph that looks very similar to that first one we saw in the beginning of the chapter. Keep that in mind. We got some other looking equations over here. Vibration of CO molecule again as the example. Molecular spectra, some more equations. Aha, these graphs as well. You see how these graphs keep recurring? I keep remembering the Paschen, Balmer, and Brackett, and all those series that we saw in the previous chapter. I don't know what this graph is. We're going to zoom through because I don't think I have enough time. I also can't check the timer because I don't want to swipe away from the screen right now. Bonding in solids, ionic solids. So cool, we go back to ionic solids and we have some equations here. Attractive. I guess they talk about energy. They try to model everything using energy. No need to, get everything in your head at the moment. Just trying to get a broad picture. We got covalent solids. So ionic solids, covalent solids. This goes back to like the first section. Metallic solids, and that is the end of that section. Free electron theory of metals. What is this? This is the Fermi-Dirac distribution function. Very, very crazy function. Fermi and Dirac, really cool guys. We don't have too much time to take a look at this now. It's a pretty complicated subject, but pretty much the graph looks like this. A graph of the Fermi-Dirac distribution as a function of energy. No need to remember that, like I said. So just remember Fermi-Dirac, and remember you're talking about solids and energies and stuff like that. I think that should be good enough. So we got Fermi energy of gold, deriving equation, some examples here, and boom, band theory of solids. I think we're almost done here. We've got some other kind of quantum mechanical looking functions here. Psi with a little plus, psi with a little minus. They both have a little subscript S. We got some other crazy looking graphs and some other even crazier looking fork or branch type graphs. I don't know what these are talking about. Let's check this out. Energy bands of sodium crystal. Blue represents energy bands occupied by the sodium electrons. Okay, we don't have time to look at that. Let's zoom through. Electrical conduction in metals, insulators, and semiconductors. I think we're nearing the end. We have 3 more sections. Semiconductors. Oh, man. This is too much stuff to go through in 7 minutes. Semiconductor. Just remember. I knew that was incoming. Anyway, that was the timer. Just remember semiconductors, solids, bonding of solids. We got semiconductor devices. So they introduced semiconductors in the previous section. Now we talk about semiconductor devices. The junction diode, what does that mean? We got some other stuff. Light emitting and light absorbing diodes. LEDs, interesting. Everybody knows what an LED is, right? You've seen little LEDs glowing and stuff here and there on electronic devices. Maybe you've also heard of the word transistor. Anyway, my 7-minute summary ended, so I don't want to spend too much time on this. The integrated circuit, superconductivity. Take a look at this graph here. It looks crazy. Superconductivity is going to take a while to explain deeply, but here they kind of just introduce it with a couple of paragraphs. And then we got the summary. So a little bit of a 7-minute summary on my phone. I hope it wasn't too kind of nauseating to look at me zoom in and out of stuff, but let's summarize the chapter with these concepts and principles. So I'm not going to read all of this, but check out these bold words. These are 4 different types of bonds we saw. Covalent and ionic bonds, and then we have van der Waals bonds and hydrogen bonds. They're in bold, so if you're studying for the test, it would be good to write these down on a piece of paper and just define them, check on Google, Wikipedia, ask ChatGPT what are these, and kind of have an idea of what the differences are between them. And also, you could read this. This should probably tell you, but I'm not going to read that whole paragraph there. This little box here is talking about rotational energy of a diatomic molecule, and it gives you the equation over here. I is the moment of inertia. We have rotational quantum numbers. So those are what the J's are. Rotational quantum numbers. That is J over here. You see that? I don't really got too much to say about that. We're just doing a little summary. The allowed values of the vibrational energy of a diatomic molecule are, boom, where V is the vibrational quantum number. Okay, some more energy equations. Bonding mechanisms in solids can be classified in a manner similar to the schemes for molecules. For example, Na plus and Cl minus ions in NaCl form ionic bonds, whereas the carbon atoms in a diamond form covalent bonds. The metallic bond is characterized by a net attractive force between positive ion cores and the mobile free electrons of a metal. Okay, I guess this whole thing here, they're bringing in ionic and covalent bonds, and they're trying to explain how metals are formed. You know, the bonds between metals. Like in a gold ring or, you know, a metal car frame. Cool. So we have the free electron theory, which is pretty deep. This is where they introduced the Fermi energy, the Fermi Dirac distribution. I don't have too much to say about that. It's going to make the video really long, so we're just going to zoom through that. In a crystalline solid, the energy levels of the system form a set of bands, and they put bands in bold over here. Electrons occupy the lowest energy states with no more than one electron per state. Energy gaps are present between the bands of the allowed states. That may sound like a whole bunch of nothing, but just keep in mind we got bands, we got electrons, we got crystalline solid. Just have these words kind of ringing around in your head so that when you're doing the homework, it's not like brand new to you. This is why the 7-minute summaries are important. And then we got semiconductors, semiconductor devices, a whole bunch of stuff that we cannot get into. So boom, that is the chapter. Let me go back to my bookmarks. This was chapter 43. So we got 44, which I have not bookmarked yet, 45, 46. And yes, thank you very much for watching. I hope you enjoyed this phone 7-minute summary. It might be a little bit bootleg, but this is just proof of concept to show y'all that you could do this anywhere as long as you have the energy. You got 7 minutes and you got a PDF. But if you have Wi-Fi, you can find any kind of document online that talks about this stuff. So just Google search any one of these subjects and read up the Wikipedia page, and you should be chilling. Anyway, thank you for watching. I'll see y'all in the next video. I'm going to try to post all of these 7-minute summaries first, so then I can just focus on some problems and stuff. Let me know in the comments if you're interested in any of this. Let me know if you have any questions. Peace out.